ಬೇಡ ಮುಗೀತು.
Welcome to the Machine Learning Track, and I'm your host, Priyanka. So let us begin our session with an interesting question. Is anything possible without humans in the field of AI or machine learning? Another question, how can we foster collaboration between human and AI? So in this talk, we'll be discussing about towards human AI teaming, challenges and opportunities of humans in the loop AI training. And to deliver the talk, I would like to introduce to our speakers, Clodéric Mars and Sagar Kurandwad from AI Redefined. Clodéric Mars is currently serving as AI Redefined. He has worked with renowned institutions like Enria, Golem, Masa Groups on explicit AI techniques. Sagar Kurandwad is an ML developer at AI Redefined with over a decade of experience in leading teams, developing end-to-end custom solutions in NLP, computer vision, and AI. So I now invite the speakers to present their talk.
Thank you, Priyanka. Welcome, everyone. Let me just share my screen, and we are good to go. So yeah, hello, everyone. If you are watching us today, chances are you are using a computer. And if you are using a computer or a smartphone, chances are you've been interacting with an AI today. In fact, most of us have been interacting with AIs every day for the past 5 to 10 years. AIs that help us do a web search, AIs that help us autocomplete a mail, AIs that helps us go from point A to point B in our car, AIs that helps us analyze data, lots of different kind of AI system. And we are learning to leverage them. We are getting better at leveraging them and at deploying them. But the thing is, it's not reciprocal. Those AIs are not learning from us. I mean, they do learn from data sets, and sometimes those data sets have been annotated by human, but they usually stop learning once they are deployed. They don't have a chance to learn what it is to interact with the human, to learn from those interactions, to see how the human react to their recommendation, to their prediction, and to leverage what humans can bring to the table. And I mean, it's too bad, because there is lots of use cases that would benefit from having a dual approach from AIs and from human. On one side, the human bring to the table their sense of common sense, their sense of context, their ability to take social cues. They are generalists. They can take what they've learned on a specific domain and apply it to another one. And they are being trusted to make lots of hard decisions. On the other side, the AI have an impressive capability to process a lot of data, to make decisions, to be consistent, to really know how to achieve a specific task, and they can be tested, they can be validated. So ideally, we would like to take the best of what an AI can bring to the table and take the best of what the human can bring to the table and create a team of AI and humans to tackle those big use cases. So myself and my colleague, we work at AI Redefined, a Montreal-based startup. And our mission there is to add context to artificial intelligence thanks to our human AI orchestration platform. And we will go more in detail about this human AI orchestration platform. At AI Redefined, we are in a unique position to tackle those big problems because we have dual expertise. We come both from a world of artificial intelligence, both in academia and in the industry, and also from the world of the game industry and simulation industry, where we have learned how to create interactive software and software that interact with humans. And we tap from both of those experiences to create what we'll be presenting today. So what's our approach to create those human AI teams? We think the needed step is to create common experiences, basically to put human AI inside environment and let them interact with the environment and interact with each other to learn from each other. We start from simulated environment, where you can explore a way to fulfill a task. AIs can make mistakes, but they can also discover new ways of solving a particular task while interacting with their human counterparts. And when everything starts running smoothly, we can graduate to real environment. But the key is to never stop learning. Before deployment and after deployment in a real environment, the AI should continue to learn because the environment will evolve, the human with which they interact will change their behavior, and the task might also evolve a little bit. So common experiences from before deployment, during training, and then after deployment, and never stop learning. And the ability for AI to be trained by interacting with human is studied by a field that's called human in the loop learning, that's been delivering some interesting results for the past years in academia. And I selected two particular examples that I wanted to that illustrate basically what's possible in this field. So on the left side, that's a work that's been done by a bunch of US university, and they are focused on a small robotic example where they have this small robot that kind of look like a Roomba, and they are teaching this robot to perform fetch tasks, like what you would teach a dog to do. And they are training this robot from scratch only by interacting with a human trainer that provides real-time reward when the robot is doing the right thing, is catching the ball, etc. And through this interaction, in less than 2 minutes, they're able to train on all those tasks. On the right side is a work by DeepMind and OpenAI. And it really relates to this idea of reward that I touched upon just previously in the context of reinforcement learning. So let me give you a little bit of context. So reinforcement learning is a particular style of machine learning that we actually really are inspired by in our work. And reinforcement learning is about putting an AI agent inside a simulation, and instead of training him from example of how to fulfill a task, you give him this environment, this simulated environment, and a way to measure how close he is from fulfilling the task. And the agent will learn by trial and error. And when he's trying something that gets him closer to the goal, then he will try to learn about that thing. And when it's getting it farther than the goal, then he will learn that it's not the right place to go. And this measurement, how you evaluate how close an AI agent is to the goal, it's what we call the reward function. And designing, implementing a reward function is not trivial. It might be very complicated because you have to take into account potentially different sub-goal, different measure of how to fulfill the task that's given. And you also need to make sure that there is no local minima, that there is no edge cases where the AI could get trapped into and no longer be able to learn outside of those edge cases. And so really, it's a complex topic, designing those reward functions. And so to go back to the work I was talking about, those guys from DeepMind and OpenAI, they basically got completely rid of this reward function and replaced it with interaction with humans in two forms. First, the human provide demonstration on how to do the task, and then the human are able to give preference about different approaches the AI is taking to fulfill the task. And so they evaluated this approach on a collection of Atari games, which are a standard benchmark in the reinforcement learning world. And they've shown that without any reward function and with those interactions with humans, they're able to first get the state-of-the-art result on those environments and even solve environments that weren't previously solvable. So really, human in the loop learning is a field that already delivers. It has really interesting results, and we can use those results to help us train AI in these common experiences and get better human AI teaming. But human in the loop has a fair bit of challenges. The first category of challenges are about the limited resources, the fact that humans are limited resources. When I say limited, I mean in contrast to machines. In a reinforcement learning, the machine and the agent can experience years of experience in matter of minutes because they can play at superhuman speed. As soon as you put a human in this system, you no longer can run at superhuman speed. So you have to make sure that the time the humans are spending with the AI count. The first aspect of that is the limited availability of the human. They can't work 7 days a week or 24 hours a day. And more importantly, they can't really focus and give good input and good interactivity for a long period of time. So you have to pick and choose. The first aspect is to make sure that the human interact with the AI when the AI are at the right stage of learning. So in practice, it means that you would want your AI to train with themselves first, and then once they get a basic grasp on the task that they are supposed to fulfill, then involve human in the training when their input counts the most. The other aspect is to crowdsource. Basically, instead of having a few humans, have a lot of humans providing interactive feedback to those AI. Of course, you have then engineering problems and data quality problems. The second aspect of those challenges is more of an opportunity. Humans can provide information in various modalities, and to make the most of the time that you have in front of those humans, it's important to be able to leverage all those modalities, which means that you can't really use an algorithm that will only train from reward and only train from demonstration or only train from preferences. Ideally, you want an algorithm that's able to take multiple modalities of interaction and train from all of that. And it's not only about explicit interaction, but also implicit channel. Let's take, for example, if you want to train an AI agent to automate the lights in your house, for example, when the AI is turning off the light and it's not the right moment, then you could request the occupants to explicitly give a bad reward to the AI. Say, oh, bad AI, you did something, you turned off the light at the wrong time. But you might also just look at what the humans are doing, and if they turn back on the light, then interpret that as a contradiction of what the AI agent did and as a negative reward, and an implicit negative reward. And those implicit channels are sometimes much more efficient than the explicit one because they are just natural to the way the human interact with the environment. But of course, they pose some UX challenges this time. Last but not least, the human needs to have a stake in the training of those AI agents for them to give their best during this interaction. One easy way to do that is to create an apprentice-mentor dynamic between the AI agent and the human, and that's really the case when the humans training the AI agent and continuously training it are the ones that actually work with the AI agent and whose work rely on those AI agents. And you can do that from the very simulation before deployment and up until continuous deployment. And the other way to deal with that is to gamify the training process. And here there is a bag of tricks that come from the game design community that you can leverage. The other set of challenges are more technical. So since the beginning of the presentation, we talked about machine learning frameworks, and there's a bunch of them. We can also include other kind of AI framework stuff like heuristics, decision-making, planning, solving, search, that also have their place when it comes to creating the best team up between AI and humans. We also talked about environment, simulated environment. So you can imagine industrial simulation like Simulink or game engine or any kind of physics-based simulation, but also real-world environment. And there it's about digital twin, it's about IoT, etc. And last but not least, all those systems need to interact with human through user interfaces. And that also brings to the table UI framework, web UI framework, game engine, and the likes. So there is a lot of different moving pieces that works differently, that comes from a different software engineering tradition. And it's kind of a mess to make sure that everything works together. the way we found that work well is to basically isolate all those worlds together and create some kind of central orchestrator that let all those pieces work together. So yeah, there is those challenges, and you need to address them. You need to make sure that you make the most of the time you have in front of the human, and you need to make sure that the system you design can actually integrate all those moving pieces. But once you manage to address those challenges, you can get to the really interesting part, which is designing a collaboration system with AIs and humans, and put in place a virtuous circle where the AI is learning from the human, being able to leverage its expertise, its sense of context, but also where the human is learning to trust the AI, and is learning to better to give the best information for the work of the AI. And to help the industry and researcher to go to this stage as quickly as possible, we are developing Cogment. And Cogment is an open source platform. It's designed to train, operate, and deploy AI in environments shared with humans. And Cogment is basically two different things. So on the left side, it's we describe this multi-actor framework, and on the right side, it's really AI operationalization platform. So let's start with the left column. So Cogment is a multi-actor framework. What does it mean? It means that it's inspired by reinforcement learning and by Markov decision process, and it formalizes how actors interact with an environment by receiving observation and by providing the action they want to take into the environment. It allows us to create an abstraction where both AI agents and humans can interact with the environment in the very same way. It allows us to support homogeneous abilities between all those actors. So, for example, the Cogment supports a swarm of drones that would be in charge of taking picture of a dam for maintenance purposes, where all the drones have the same capability, and the main objective is to help them collaborate to optimize their search space. But Cogment also support heterogeneous abilities. So, for example, let's imagine a logistical network where you have warehouses. You have, for example, autonomous truck that will do delivery between the warehouses, and you have last mile human driver that would deliver from the warehouse to the end customer. And Cogment also supports a setting where all the actors are collaborating towards the same goals, but also set up where they are competing. Maybe they have slightly different goals that you try to balance, or maybe they have completely goals that are at odds, and it's about a competition. The other aspect of this multi-actor framework is the reward part. So reward is an important part of training AI, especially in this kind of environment. And Cogment support multiple sources of reward and support retroactive reward. So what does it mean? The multiple sources means that you can balance objective goals. So let's say if you are training an AI to park a car, the objective goals would be make sure to not bump into another car, make sure to park in a parking spot that's an authorized one, and make sure to do it quick. And so those can be measured directly by the system. They are objective measurement, and they can come in real time. On the other side, you have evaluation that can come from the occupant of the car. So the occupant might be able to evaluate the comfort level that they experience being inside the moving car, and that's something really subjective. They can also provide feedback on the knowledge they have about the context. So in this case, we can imagine that they know that part of the parking spots are really likely to be targeted by pigeon, for example. And they would be able to provide a reward to steer the AI towards other parking spots. And those are really contextual, and only humans that know about this particular parking lot would be able to provide those. And so you have multiple sources. objective measurement provided by the environment, by the system, and subjective measurement or contextual measurement provided by the occupants. And the retroactive part is to deal with the fact that humans, they can't do their reward immediately. They need time to perceive and to process and then to provide the reward. And so basically when they are giving a reward, they are giving a reward regarding an action that occurred in the past. And to deal with that while maintaining the ability to learn continuously, we need special system that Cogment has to deal with this kind of retroactive evaluations. And last but not least, implementation swapping. So the way the Cogment multi-actor framework is set up, it decouples the what the actor is able to do, what action it can send, what observation it can receive, and the how, meaning which the way it generates those actions based on the observation, its implementation. And Cogment completely decouples the two, which means that once you have defined a particular experiment, a particular system setup, so which action exists, which role basically can be taken by the actor in the environment, you can swap implementation that fulfills those roles. You can replace an AI implementation by a human, and thus you can have a training regimen that starts with only AI interacting with soldier, and then some of those AIs are replaced by humans when they are available. You can create really mixed training regimen where you have several styles of AI that work together during training to better provide a good curriculum. And you can have, like we will see later, a hybrid system where you have different implementation for each of the actors, and you swap the one that makes the more sense during operation, given some regulatory or some preferences from the operator. So yeah, Cogment provide a complete multi-actor framework that helps with the decoupling, that helps with the architecture of the system, and that enables a lot of use cases and a lot of hybrid use cases, which really are important to make the most of the availability of the human. But Cogment is also a production-ready framework. It's completely tech agnostic. It's been tested with basically all the machine learning framework from TensorFlow, PyTorch, JAX, Scikit-learn. It's also been successfully integrated with several kinds of simulation and digital twin, and with lots of UI framework. It achieved this tech agnosticity thanks to a microservice architecture, a Dockerized microservice architecture where all the systems are isolated from each other, and Cogment takes care of the orchestration between all those services. All those services are distributed. They are distributed from the get-go. So when you install Cogment on your laptop, you actually install some distributed services that will be able to scale without integration discontinuity from your laptop to a cloud deployment into a high-performance computing deployment. So yeah, Cogment provides this platform, and it's a way to jumpstart experiment in human-in-the-loop learning, and also to help put human-in-the-loop learning into production. We are doing it internally at AIR, but we also provide Cogment as an open source platform to help the community do that. And you can get Cogment at this address. And now I will let Sagar present actual concrete example of what Cogment can do in those various use cases. Sagar.
Thank you, Clodéric. Hello, everyone. I'll be presenting two use cases today that demonstrate how humans and AI agents can benefit from the interactions that they can have with each other, and how Cogment plays an important role in enabling those interactions. The first example here is that of Lunar Lander. As we can see in the videos, a lunar lander is an environment which consists of the surface of the moon, and the agent here is a spacecraft. The task of the agent is to learn to land successfully on the surface of the moon in between the areas designated by the flags. Now that demonstration is available on the left of the screen, where we see an agent which is already trained successfully land between the two flags. Now, in order for the agent to learn this, um, it has to discover what actually landing means, and then it also has to identify what the environment's expectations are in terms of the location of the landing. The search space right from the start seems large, even for this smaller and less complex problem. And as Clodéric mentioned before, if we take the approach of the vanilla reinforcement learning, then what happens is the agent takes a lot of time to train and takes a lot of time to learn. That we saw in the previous slide. However, this could be improved if we get a human in the loop. The role of the human in this case would be to teach the spacecraft of how to fly, how to land, and specifically how to land between the two flags. Now, what this does is it reduces the search space uh, for the spacecraft. And instead of searching the entire space and accidentally discovering what landing means and what the environment expects as far as the location is concerned, it is actually demonstrated by the human to the agent. As we can see on the video in the left, but the agent takes control of the spacecraft and tries to land it in between the two flags. This provides valuable demonstrations to the agent. As a result, the agent is able to learn quite quickly compared to the vanilla reinforcement learning framework. And this is quantified by the graph on the right. The x-axis is the number of trials, and the y-axis is the rewards that are accumulated at the end of the trial. The blue curve indicates the vanilla reinforcement learning algorithm that the agent uses in order to learn in the environment. As we can see, it takes a lot of time for the agent to discover what landing is and where to land, as a result of which the convergence is slow. But once it figures it out, it consistently performs those actions in the environment, thereby accumulating more rewards over trial. However, if we introduce a human in the loop, which is demonstrated by the red curve, we see that the agent is able to accumulate scores very quickly and converge to a very good score. Even after the human is removed from the loop, after providing demonstrations, as we see by the yellow curve, we see that the agent is able to consistently outperform a vanilla reinforcement learning algorithm and is able to exploit its learnings from the demonstrations that were provided by the human. So in this way, human inputs can be used to speed up the learning process of the agents. Humans provide prior knowledge that agents do not have, thereby reducing the search space and allowing agents to learn a task quickly. As we see in the next slide, uh, this benefit is what human provides to an agent. And the implementation is made easy and convenient with the help of Cogment. Cogment here is colored in blue. The orchestrator, which is the heart of Cogment, allows for seamless interactions between the actors and the environment, which are demonstrated in yellow. The spacecraft actor and the human actors can interact via the orchestrator. Human actor can provide demonstrations by interacting with the spacecraft and taking control over it in the environment. And the spacecraft actor could learn from its past experiences with the help of activity logger, which gets generated by the orchestrator as the trial proceeds. Um, Cogman makes it seamless for integrating different implementations of the actor services and the environments, and hides all the complexities from the end users. Now, this is an example where the humans benefit agents. Next, we go to a more industrial use case where trained agents benefit humans, and this use case is that of smart responder. Smart responder is a 911 emergency response environment. In this environment, human operators receive requests for emergency services that they need to answer by allocating various dispatch units to the respective events, as we see on the right side of the panel on the map. More often than not, human operators are overwhelmed by the frequency at which events are generated in the system. As a result, there's a lot of backlog that piles up and that needs to be addressed. Additionally, it is possible that major events consume more time of an operator, thereby allowing more events of minor severity to pile up in the system. And it is this bottleneck that can be cleared with the help of AI. It is the responsibility of an AI agent to make sure that there is limited cognitive load on the human, thereby allowing the agents to take care of a bunch of these minor tasks and ensuring that the queue of backlogs is kept to a minimum. As we see next, this is a vanilla setup of a 911 response center. On the right, we have the UI or the system through which a human operator could interact with the system, uh, dispatching units which are available on the map to the events which are also displayed on the map. The human operator is not the only actor in the system at the moment. There is also a dispatch agent. Once an assignment has been done from a dispatch unit to an event, the dispatch agent is responsible for providing an optimal route from the dispatch location to the event location. However, as mentioned before, if the performance of the system goes performance of the system is impacted with a lot of cognitive load, in that case, there's a queue that piles up of the activities that there are in this system. This can be addressed with the help of an assignment operator. The assignment operator looks into various events that are there in the system and the available units, and then recommends those to the human operator, as we can see on the left panel of the right screen. A human operator could either confirm these assignments or dismiss them. If the human operator confirms the assignment, then the assignment directly is provided to the dispatch agent, and the events are handled in the system. Whereas, if the human operator dismisses it, then that information is flown via the human operator, and the human operator manually overrides and provides the instructions of dispatch. This again is an issue, especially when human operators are busy on one particular call and are unable to confirm or dismiss the rest of the uh, recommendations that the assignment agent has. And hence, we introduce an autonomy level. The autonomy level is a toggle that allows the human operator to keep it between low and high. And when it is high, it provides high autonomy to the assignment agent to take over the dispatch responsibilities of the minor events, while the human operator takes care of the major ones. As we see, this is also insufficient for human operators in the field, as the time that human operator spends on a particular major event exceeds a given time. It is not possible for the human operator to sometimes go back and toggle the autonomy level between high and low and maintain the system's optimal performance. And that is why we introduce the dynamic autonomy agent. Dynamic autonomy agent reads the response statistics of the human operator, as well as the stats of the events and the dispatch units available, based on which it decides to toggle the autonomy between high and low in order to ensure that the entire systems work smoothly and there's a constant cognitive load on the human operator. The human operator now can focus on major events And even if the major events take more time, the system is optimal in its performance as the assignment agent is able to clear a majority of the events which have minor severity. The queue length is maintained to a minimal, as we can see on the top right of the right panel. Next, what we observe is that the system is a hybrid system. It has a dispatch unit, which is basically a path planner, which is not non-learning in nature. We have an assignment operator, which could be learned, or it could be just a physics solver. We also have the humans and AI agents, and in this particular context, AI agents specifically act as a glue between human operators as well as the learning slash non-learning algorithms, thereby allowing the system to perform smoothly. And hence, this is an example, as we see next, where the agents are responsible for helping humans maintain the flow of the system without any blockages. Like before, the implementation is made easy with the help of Cogment. The orchestrator here allows seamless communication between the human operator and the environment on the left to all the agents which are on the right. In addition to the activity logger, which can be consumed by these agents in order to train themselves, there's also a dashboard that allows the human operators to monitor the performance of the agents during and after training. As we see that this is all the complexities here are under the hood, and there are various technologies that can be combined in order to solve the problem, and all the complexities of interactions and distribution of training and execution are kept hidden from the end users. Now, this is an example of an ecosystem where we have multiple agents and humans interacting, and that is what Clodéric would be presenting next. Thank you.
Thank you, Sagar. So yeah, as we've seen through those examples and through what we presented before, there's really a need and an opportunity to create collaboration, team-ups between AIs and human. And it's not just about human training AI or AI helping human. It's really a full ecosystem where you have multiple AI agents. Some of them are learning, some of them are using search techniques or constraint-based techniques or even heuristics, and between those AI agents and between humans that will provide their expertise and their sense of context to the full system. So we really believe that we have to shift our perspective. We have to stop just trying to develop AI agents that will provide recommendation or that will provide prediction. And we need to start thinking in terms of ecosystem, thinking about how we can create teams of different AIs with different characteristics and with the humans that are already in place. And that's the next big shift to create AI systems and AI intelligence ecosystems that can address more and more use cases to the benefit of the humans working there and humanity in general. And that's why we build Cogment. Cogment is built as a catalyst for this evolution. It takes care of some of the modeling challenges through its framework, and it takes care of most of the engineering challenges. And it really is there to accelerate this transition and to provide the basic tools to help both researchers, but more importantly, practitioners in the industry to embrace this new step in human AI collaboration. So like I mentioned before, Cogment is open source. You can retrieve it on our GitHub pages. And AI Redefined, our company, provides commercial version that gives additional services on top of the open source version. And we also collaborate with our customer to better design their intelligence ecosystem and help them train them. Thank you for your attention. We are a little bit ahead, but we are ready to take questions. Thank you.
Yes, if you have any questions, please type them in the Q&A box. And this talk, especially the lunar lander example, really made the talk very simplified. I could easily understand the collaboration and how it fits in. So
Yeah, that was the idea that we had with the demonstrations in order to make it clear to ourselves and everybody what human interaction looks like with an agent. Uh, yeah.
so in the chat we have no questions, but love what you're doing. We'll definitely try it out. That's what um, we have received. So as of now, since we have no questions, so I would like to thank you and end the session with a thank you note. Thank you, speakers, for such an insightful session, and I sincerely appreciate the audience for their attention and interest. Lastly, the good news for the attendees is that the most active attendees who rate session leave comments, they will be awarded with ebooks of their own choice by a Knowledge Partner Pact. So the organization will contact you, the most active attendees, after the conference. Do make the most of it. And thank you for joining the ML track.
Thank you for inviting us.
Thank you.